So we'll talk to you about space weather and the polar regions, and we've got Ken. And I'm going to say space weather really affects all of you, all of us. You might not know that in very many ways, but I'm going to try and sort of bring that to your attention and explain the ways in which it does affect all of us. And this is a sort of a slide, not to scale, but you can see the sun on the left, and you can see the Earth on the right-hand side, and you can see the Earth has a magnetic field which extends out into space, and it has an outer boundary. And lots of material flow away from the sun, and they encounter this outer boundary of the Earth, the Earth's magnetic field, and they disrupt the Earth's magnetic field, tear it open, distort it. And I'm going to show you a couple of videos which illustrates what we think actually happens. And that will generate a huge geomagnetic storm which disrupts modern technology. It disrupts satellites, communications, GPS signals, disrupts our power supplies, and a number of other modern technology which relies upon those systems. So it's very important. Let me give you an overview of what happens. So we're going to start at the sun. I have a video here. And I just love these videos because I think there's real data. It's looking at the sun. This was from 2012, and there was a very big event on the sun in 2012, which just missed the Earth. But you can see some of the kind of like you speed it up, you can see some of the sort of emissions, filaments, things happening. We have bright areas which are giving off radiation, light, ultraviolet light, so on. And active, and I'm going to play you another video which shows that again but in slow motion. And I wanted to show you one thing in particular, it's a coronal mass ejection. Look at this region here, and it lifts off. Yeah. That is one enormous great region. And we call that a coronal mass ejection. So what it is billions of tons of charged particles which are thrown out from the sun, and they draw with it the solar magnetic field that goes out into space. Now if that comes in the direction of the Earth, then that actually can trigger a large geomagnetic storm. We get a huge great disruption. That was a real event back in 2012. I think yes, there we go, yeah. You can see that go. That in 2012, it missed the Earth. It just gave us a glancing blow when it came from sun to Earth. But we think if that had hit the Earth, we would have had what we call a 1 in 100 year event. Something which is really quite extreme, that doesn't occur very often. And that is what our government is really concerned about, and really work that we actually prepare for events like that. You might remember those the tsunami which caused the nuclear disaster in Fukushima years ago. You might remember the volcano in Iceland years ago that disrupted all the air travel across the Atlantic. There are examples of a 1 in 100 year event. Something doesn't happen very often, but when it does happen, it has a huge impact. And our government woke up to that and decided space weather, that sort of event which when it hits the Earth could have a huge disruption. And they put it on the National Risk Register, and that means there has to be assessment of what the impact will be, and government departments have to take action, they have to have mitigation plans. And my role as a scientist and with my colleagues that I work with is that we try and help to assess not just the space environment, but what all those impacts are. So government departments can take action to mitigate, reduce the impact. Okay. So here is, I'm going to show you another video. Now this is an artist's impression of what we think actually happens. So we have that coronal mass ejection on the sun. Billions of tons of charged particles dragged through the solar magnetic field. When it reaches the Earth, here's the Earth's magnetic field. It rips open the magnetic field on the base side, draws it across the polar cap, and then energy is loaded and then released quickly from the magnetic field into the charged particles and come down the field to create a new order. Let's see that again very quickly.
Yeah.
Yes. Here we go. So here's a coronal mass ejection being emitted from the sun, coming towards the Earth in this example. Sees the Earth's magnetic field, rips it open on the base Earth, draws it across the polar cap, and loads energy into the magnetic field here and is suddenly released. And this cycle goes over and over and over again in a large magnetic storm. So the magnetic storm may last 2-3 days, can last as long as 5-10 days, typically. But usually it's around 2 or 3 days, and then we have a recovery period. And it's when that happens that we have disruption to our power grids and a whole range of other things. Okay, I've got time to show you that. So this shows you a range of systems which are affected. Damage to spacecraft electronics because of those charged particles which are accelerated when the Earth's magnetic field reconnects. Disruption to the communications systems, the GPS signals, for example. We all use GPS signals in one way or another if you're just doing navigation in a car, something like that, for example. 40% of all the trades on the UK stock market use GPS signals to time the trade, the trading on the trading floor. So it's really important. And there's lots of course businesses which use GPS in many different ways which we never envisaged originally. And cause additional radiation to aircrew and passengers, which has to be monitored and is regulated. And can affect the electronic systems in aircraft on high latitude polar routes. Not equatorial, but high latitude. Most important of all, I'd say, is our power grid. You can set up electrical currents on a power grid. And there have been examples when in Quebec in 1989 when there was a power blackout for the whole of Quebec. And in 2003 in Sweden, areas which were damaged. I'll show you the example in a moment. So our government is really focused on the damage and disruption to the power grid. Not just our government, but the US and all the kind of northern hemisphere. And New Zealand, not to forget, this also occurs in the southern hemisphere as well. New Zealand put a lot of effort into protecting their power grid now.
Telluric currents.
Yes.
What are they?
Okay, I'll explain the next slide actually. I wanted to. Okay. I will come to your.
It's not water, is it?
It's not water. Certainly not water. No. So we define space weather. If you want a one-liner, changes in the space environment that can damage and disrupt modern technology and they endanger human health. Okay, and let me just give you a financial input. So there was an American study done back in about 2009, estimated a severe space weather event, if it took place, could end up with something like $2 trillion in losses. Now, a lot of us kind of feel that was an estimate, and it was done a long time ago, and I think we've kind of refined that down a bit. There was an important study that was published a few years ago as part of it, estimating the losses to the UK for one of these 1 in 100-year events occurred. I think it's something like £2.9 billion it will cost us. And if we invested in doing more forecasting, we think that better forecasting means you can take better action to mitigate the effects, and you could reduce that impact down to 0.9. So I was part of a program, it's called a swimmer program, where we actually developed a £20 million program, and we had various universities up and down the country and the UK Met Office and other government research labs involved in trying to develop mitigation processes, forecasting, and actually understand what the impacts are. And that's just come to an end. And we deliver all our results to the UK Met Office, which is the main part in the UK that does the forecasting. Okay, I'm coming to your answer to your question, but I'm doing 2 slides, I haven't forgotten. So this is, I wanted to show a picture of the aurora. You may have been able to see the aurora in Cambridge actually last May. I hope many of you did. I mean, it is beautiful. Particularly if you have to go somewhere really dark to really appreciate it and see it. I'm glad so many have been able to see it. This is our base in the Antarctic. This is Halley. And this is speeded up, as you can see. You can tell the stars going by. It's all speeded up. But I wanted to put that in just to say that this is in the Antarctic. It was in the Antarctic winter. And we do have beautiful displays down there. We make measurements of the aurora and the current system. So, and just to give you an idea of what it's like in the Antarctic. That's not photo. When I first saw a photo of this, I thought it was photoshopped. It's not. It's just amazing. I've been down there on that base. I'll just say one thing, because this is the working areas are actually over here to the left, on the right side, where all the labs are. This is a kind of like the big accommodation blocks. Bedrooms are over here. This is a big accommodation where you kind of live. And these are kind of like these generators in here. And the designers, when they put this together, they said, okay, when you go to work, you need to come from here, and you need to go out into the open, and then you go here. And then you do your work, your research, and so on. And then you come back again for lunch, and you go back, and maybe go for coffee, back. But you go, so the idea is you go outside, you go to work, you come back. Now when it's minus 25, of course you put all your clothes on and everything, and then you walk, I don't know, 100 yards, 100 metres. It's less than that, maybe about 50 metres actually. And then you take all your stuff off, and you get fed up of doing that. You don't want to do that. So in the end, you go with your t-shirts, because it's warm inside, and you open the door, and then you just run as quick as you can and get to the other side. That's what you do in practice. Does that make sense? So, the aurora. This is from a great magnetic storm in 1989, one of the biggest we've seen. And this is from a satellite looking down. You can see the outline of the Antarctic here. Our base, Halley, as I was just talking about, is here. And you can see the aurora all the way around. And you can see it's a huge extent. I'll show you 2 areas. This is in the northern hemisphere. UK is over here, Greenland, America, USA, and you can see. Now, normally the aurora's up here, but when we have a magnetic storm, it expands equatorward. It covers a huge, great big area. And it's one of the most visible things we can see of a magnetic storm. You can see the aurora. Now, it's beautiful, but behind that, if you're a physicist, you look at that and think there's huge electrical currents which are flowing through the aurora. They come down from space, through the atmosphere, and out again. And when I say large, I mean they're millions of amps. So you might get, 13 amps out of a plug? 13? But these are 1,000,000 amps flowing. And it's flowing at about 90 kilometers above your head. And these currents are not steady, they're always changing. They change in intensity, they change in location. You see the aurora and you see how it moves. Now, how many people, I wonder, might remember back to your physics days at school when you learned physics, maybe? Okay, so if you have a current which is moving, it has a magnetic field associated with it. And that magnetic field will permeate the ground. And that magnetic field will then set up, if it's changing, it will set up an electric field in the ground, in the rock. And that will then drive a current in the rock, magnetic to the So that's really what it's about. So that changing aurora, changing currents of a magnetic field sets up an electric field, sets up a current in the rock. Now that current, of course the rock is quite resistive. The current finds it difficult to flow through the rock. But when it flows, it can find a transformer. What it does is it will go up through the transformer and along the power grid, along the power lines. And that's what we call, in this case, we call them geomagnetically induced currents. Or if you're in a pipeline, they use it to direct currents. Okay, it's effectively the same thing. Now, our power grid, of course, it carries huge electrical currents, but it's an AC current, it's alternating, it's always changing. When the aurora comes along and generates these currents, these are direct currents, okay? And that's a very different thing. So they shift the whole level of the current system out of the design specification of the transformers in the system. This is what happened in Quebec. This is a transformer, and within about 90 seconds, this is burnt out because it causes heating inside the transformer, and that actually can then, if it's not disconnected, you can see what happened. It burned the whole thing up. So you have to try and protect against these things. 6 million people without electricity for 9 hours. There have been similar things in 2003. We had a very big storm in Sweden and in South Africa. And in the May storm last year, we took mitigating action to try and prevent this in the UK. So there was disruption, but it didn't cause blackout, a regional blackout. Same in New Zealand. So we're trying to build in resilience. We're trying to protect the systems. So that's the sort of thing that can happen. Let me move on to something else, satellites, charged particles. So we use satellites or indirectly in our everyday life all the time now. But here's a plot. So this is a plot of the Earth, and it shows these regions of red are regions where we have very high energy charged particles, electrons, and they're trapped by the Earth's magnetic field. And the particles are bouncing up and down, and they circulate all the way around the Earth. For scale, I've put in the GPS satellites, sort of flying right the way through the heart of this region. Okay, in here. And out again. The geostationary satellites are geostationary orbit, which are used for mostly for communications, telecommunications, some weather ones as well. They're on the outer region. The space station flies down here. Okay? They very carefully avoid these regions. You don't want to go through these regions, it's not good for you. So that gives you an idea of scale. So these charged particles will damage the electronic components in spacecraft. And the levels of these particles are always going up and down. Okay, this one. It's okay. So, now, part of the work that we did in the Antarctic, I want to bring in the polar regions again, is that we have special kinds of radio receivers in the Antarctic. That's me in front of one of them. You can see the tower and the wires which measure special types of radio waves. There's a Halley, and it detects special kinds of radio waves. I'm going to see if I can find it there. Yeah. Can you hear that? So those are signals which have come from space, from the radiation box I just showed you. They're guided along the Earth's magnetic field down to the ground. And we pick them up in Antarctica. Here's another one. That's a whistle. That actually originates from a lightning flash in the northern hemisphere. The signal might have a thunderstorm, a lightning flash, and the signal goes out into space. It's guided by the Earth's magnetic field, comes back down to the ground in the Antarctic. So by studying those waves on the ground, we can then actually say about what's happening in space. So we're doing remote sensing, we're doing it in the opposite direction, if you like. So here's another little video, try and put that together. So here are charged particles. They're trapped by the Earth's magnetic field, they're going up and down the field and bouncing. What they're doing is they're creating these special kinds of radio waves, shown by these kind of circles. And they're interacting with them. And they generate the waves, and the waves travel along the field, but they interact back on the particles and dump them down into the atmosphere. It's a loss process. Okay? So everything has an action, there's a reaction. So here we go again. They generate the waves react back on the particles and bump them back into the atmosphere. Now, all the way through from the when the radiation got discovered in 1958, so all through the 60s, 70s, 80s, and early 90s, we thought we understood how these radiation belts were created. We thought we understood how these particles accelerated at very high energies. Turns out it wasn't the whole story. So let me see here. Okay. So all that time, 60s, 70s, 80s, early 90s, the theory said these wave-part interactions would just remove the particles. But in the late 90s, myself and colleagues in California and in Canada, with a collaboration, and we actually showed these waves will accelerate the particles to very high energies, and then they're the ones that damage the satellites. By analysing our data in the Antarctic and data from satellites in space. Okay, so that was our piece of basic research, and then we developed a computer model which would then forecast periods when the numbers of these charged particles would be elevated, and so that would be risk to satellites. So here's a nice artist's impression of the satellite. The inner radiation belt is not showing the inner radiation belt, but anyway, it's a nice photo. Yes, magnetic field. And this is the sort of thing, okay, I'm not going to go into the detail, but we have colour displays that we present. This is used by the Met Office now, and also by the European Space Agency. And we can interpret these plots. When we convert them into a red, amber, green risk area here. So for this particular satellite geostationary orbit, the risk of internal charging is pretty high. And so the satellite operators would look at that, and they'd actually do things to mitigate that impact. Okay. So we turned it into something, our basic science, we've turned it into an application. We try and do something useful. As I said, it's used by the Met Office and by the European Space Agency. And it's also, I worked with the satellite insurance guys, and they were very interested in this, because something goes wrong with the spacecraft. So modern communication satellite, $250 million to build, 100 million, 80 million then to launch geostationary orbit. That's where most of the big telecommunication satellites operate. And there are over 650 satellites out there. So it's a huge amount of investment up there. The design life is about 15 years. So the insurance guys are really interested. Anything goes wrong with that spacecraft, they pick up the bill, tend to pick up the bill. So, insurance payouts, 150 million, 160 million. They don't occur very often, but when they do, it's high impact. So, and they like to have some knowledge of, was that caused by spaceflight? Was it caused by some design fault? Was it caused by some kind of engineering fault? And they like to have some independent information to assess the reason. Okay, disruption to aviation. This is another thing. We also have things called a radiation storm, where we have huge, high charged particles accelerated close to the sun, and they travel towards the Earth, and they get into the polar regions of the Earth. And here's an example where that happens. This is for low altitude satellites crossing the polar region, and the red colour is showing you where they've detected all these high energy particles which have come from the sun, or close to the sun. You can see it's in the polar region. It's much easier to access the Earth in that region. And aircraft, so here's a few examples of aircraft on high latitude routes, okay, crossing that kind of region, will be exposed to more particle radiation. And that has to be measured, because if you get anywhere close to a legal limit, what the airlines will do will be actually to re-roster aircrew onto lower latitude flights to help protect them. Or we have had examples in the past where we had a radiation storm and the air traffic control have notified the airlines and they've taken action. And in some cases to ground some aircraft to prevent them to taking off. So it doesn't happen very often, but it's important. These events also, what they do is we have communications, here's for radio waves going right the way around the world. It can cause absorption of the radio waves in the polar region. So it becomes very difficult to communicate with satellites with very high latitudes. Not all of them use any kind of like satellite communications. Some of them still have to use high frequency radio communications like this. And the signals can be absorbed so you can't communicate with things. So that also is a risk which has to be taken into account. Okay. So how big can it be? How big could one of those radiation storms be? This is kind of a research question which we and others are looking at. So now we go back to ice cores. We need ice cores to actually try and help work that out. What happens is those charged particles come in, not just from the north and south pole as well, and they go into the atmosphere and they create all kinds of radioisotopes, different kinds of isotopes. So they can create things like beryllium and chlorine. And then you have snow and rain that goes into the ice, and then the snow gets compacted into ice, and we can go back. Now we've just got our latest ice cores goes back about 1.1 million years. Okay, that's how long we can go back. So a lot of that is done for climate change, looking at changes in CO2 and changes in temperature. But we can also analyse the ice cores. There's somebody actually taking out one of them from the drill. And we can analyse the amounts of these, and we can try and work out radiation storms and when they've occurred in the past. So in 660 BC, this is one I picked out. There was an event which we estimate, or was estimated by this paper, was 10 times bigger than the largest event we've seen in living memory. Largest event we've seen in living memory is 1956, we have measurements, just before the launch of the first satellite. So in history, they're much larger events. And we have to try and work out, well, okay, if you work out what the radiation dose is and you go to the satellite operators and say you're designing your new satellites, would you be resilient to something like that? That's a good question. Don't get much of an answer either. Very interesting. So, okay, another problem, space debris. So this is much more highlighting the topics in the news now, and rightly so. So we've launched so many satellites up into space. There's something like 650,000, 6,000 satellites up on orbit, in low Earth orbit right now. There we go. Oh yes, okay. And there's lots and lots of small pieces of space debris, satellites that exploded, satellites that actually had pieces come off them. And they're called space debris. There are about 135 million pieces that could disable a satellite. These things travel really fast, 7 kilometers per second in low orbit. So you need to have a small grain of sand or something like that. They're going to create a huge great big hole because it's damage to another satellite because it's traveling so fast. 580 collision alerts in 2020. I'll show you this video. It'll give you an idea. This is from the European Space Agency. So this is geostationary arc, geostationary ring. This is sort of a GPS type orbit. But look at low Earth orbit. Everything above 10 centimeters, what's 10 centimeters, about that? Everything above that is tracked by the US system. But there's still huge amounts, smaller than that, which are not tracked, which pose that danger. So it's really important that we look at removing this stuff. It's very difficult to do, to get to work. Let me just show you, I'll come back to that point. Let me show you examples. So 500 kilometers, this is this particular spacecraft, these are years. 2006, 2007, 2008. You can see how the orbit eventually starts to come down, it'll drop. This is a SHAMP satellite. They boosted the orbit, then boosted the orbit, and once you get down below about 200 kilometers, that will re-enter. Typically maybe a day, maybe a couple of days. It's uncertain because of the orientation of the spacecraft with respect to its motion. So, and you don't want a huge great big piece of satellite coming down over a populated area. There have been examples of that. And there's a very big one called MDSat that ESA put up. And they had fuel to try and deorbit that to the end of its lifetime. But unfortunately, something went wrong. All the fuel was spent, and now it's going round up there. And they're going to have some kind of mission to bring that down. It's as large as a bus. You know, 20 bus. So the amount of debris is just increasing. Last year, in the May storm, this is from the National Space Operations Centre. We had a storm here the 10th and 11th of May. It was a large geomagnetic storm, one of the largest we've had for 20 years. So, at that time, you can see the Space Operations Centre, they issue warnings to UK licensed satellites if there is going to be a conjunction and they may have a risk of a collision. And one of the operators will take action to move their spacecraft. See what happened in May. That comes down about 1,900, went up to 2,500, and then down again. Okay. That was because the magnetic storm, what happens is, we're back to the aurora again. That aurora, its electrical current, heats the upper atmosphere. The upper atmosphere expands upwards. So the pieces which fly through it, and now it changes their orbit slightly. And they're all their orbit's all been changed, so the predictions are out. And it causes a whole lot of uncertainty. During that storm, there were almost 5,000 satellites, mostly I've got my name. The space, the low Earth orbit ones that Elon Musk's satellites. Thank you, Starlink. Most of them, they all have an autonomous way. So if they think they're not where we're supposed to be, they'll throw their thrusters and start moving. There are almost 5,000 of those at the same time, all moving. And that's a new risk which we're encountering. How do you do that and ensure everything is safe? So the risk of collision will go up. So that's a new challenge we have to think about and deal with. I'm conscious of time, I'm going to have to go a little bit quicker, I'm sorry. Okay, disruption to global navigation signals. This is another plot I've taken from the May storm. The height of the storm over America, you can see the sort of red hashes here. This is where the GPS, which gives you position information, the errors exceeded up to about 60 meters in error in your location. And that caused problems to the farmers because they need centimetre accuracy to plant all their seeds and fertilise everything. You might have heard that in the news. So completely disrupted it for a couple of days. Having said that, there's not much you can do about it. If you can forecast this stuff, you can warn them. They don't waste their time. That's what we can do. So that's why warning and forecasting, making that better is important. The solar cycle that I'm coming to towards the end. Okay, actually I should have updated that. I'm sorry I didn't update this. This was the projection of the next solar cycle, or current solar cycle, sorry, 2025 is here. This is what's actually happening, and actually we're over here now. And this is higher than prediction. And we still have a long way to go during the declining phase of the solar cycle in the next few years, where there's space weather is going to be a risk. So I'll summarise them and stop. Modern technologies become vulnerable to space weather. It affects our power supplies, can affect us, aviation, satellites, space debris, communications, GPS signals. We're doing lots of work to assess the impact. I run a committee in the UK, and we provide advice to government departments in space weather on what the impacts would be and some of the mitigation. I hold that twice a year, and I have regular updates with the government departments. And we need, one of the key things we need to invest and have better forecasting, develop better models, so we can help people running critical national technology infrastructure, so they can actually be warned and take action. That's it. Thank you very much.